Thank you very much for coming this day after the trip, and thank you for inviting me. It's a pleasure to be here. So this morning, these 3 talks in the morning are all within the same field, namely this concurrency and our model for concurrency. So I will be the one who tries to explain what we're doing in this field. So I'll do that before I get to my stuff. So this is, so I didn't put that as a bullet point. So I'll start with the introduction, and then I will get into Heiting algebras, which I will explain what that is, because I'm not sure everyone knows. And then in the end, I will get to a new thing that's been happening at our department after we explained them what TDA is. So you never know what happens when you tell people about TDA. So this is sort of a very simple example of what we do, and of course it's a playful example, so it's not. But it's it's called the Dining Philosophers, and I added in a woman. So so all these philosophers, for some reason, they want to eat spaghetti with 2 forks, and as Matteus remarked yesterday, it should be rice and then chopsticks. But anyway, so imagine they want to eat spaghetti with 2 forks, and they are sharing these forks. It's slightly disgusting. And everyone wants to pick up their right fork, then pick up their left fork, eat, put the forks down, one after the other, doesn't matter, and then think or drink, whatever. So, and it's not hard to see that since these resources, which I'm now going to call them the forks, can only cater for one at a time, there's an immediate deadlock if everyone picks up their right fork. No one can move after that. So this is sort of the basic, it's a very basic question in concurrency, and you use it to test programs. Can you find this deadlock when you have 580 philosophers and don't know the names of them, and so on. So it's, but this is sort of the idea. Then you can make more complicated individual programs. These guys all want to do the same thing. You can have resources with higher capacity. Then in this case, if they just had capacity 2, there would be no problem. I mean, 2 forks everywhere. There would be no problem, no deadlock. So that is sort of the realm we're in. So it's different from what Morris was telling you about. Morris was talking about transformation of information. This is a slightly different point of view, but it's still this problem that once you have more computers, more processors, and so on, a Turing machine is not the right model. You don't use a Turing machine, and you can't use a number of Turing machines either because of the interaction. So in Morris's case, the interaction is through information. Here is through these shared resources. So that's the difference and the connection in some ways. And so now I'm going down to only 2 of these philosophers. So A is one of the forks, B is one of the forks. So the programs look like they're not the same, but that's because one guy's right fork is the next guy's left fork. So what is the model here? The model is that we have processors or different computers along each axis. They have a time. There could be loops and forks and so on. Again, this is a very simple example. So along this way, this one wants to access resource A, that's the P, access resource B, that's and then release, that's a V, release B, and then release A. And the other one wants to do it in the other order. So what are then the blue rectangles? The blue rectangles are states that are not allowed. Because if you're within the rectangle labeled, it's labeled a capital B, which is not very pedagogical because the resources is not capital B. But the one labeled capital B means if you're in there, it means that 2 have access to the resource B, and you cannot have that. So these blue areas are forbidden states. They're places where you cannot be. And so you should think about the square in the middle as joint states of these 2 processes. If you're at a point there, one of them has got to, well, the x-coordinate, and one of them has reach the y-coordinate of this point. So this is the idea, or this is the model. Now we model this continuously, and that is of course strange, because in computer science you only have sort of incremental steps. So why do we do that? Well, the philosophy here, or the idea here, or the reason is that we want this to be robust to subdivision. What has to be robust to subdivision is equivalences. So, I mean, I did a little bit of PDF annotated yesterday, so a lot of this is handwritten. It makes it sort of, what did you call it, Roy, more artistic. so there's sorry about that, but so you have handwriting. So here, there are models where if you think that x, y that they can be permuted, it's the same as yx, you would put in what's called an independence tile. So it's just mark that this is the same. So you have to tell that for all these, that this commutes with that. But if we instead say that this whole thing is filled in and you can go through the whatever way you want to, we also include the relation over here, that if you subdivide one of them, so this one is subdivided here, then you can also go there, and then go there, and then go there. That's the same as going there and going there. So you get more. So the fact that we have this continuous model, that is to make sure that it's robust to subdivision. So that's why. And of course you can think about these as very small incremental things. But so you should think that this sort of crude picture has a lot of subdivisions, there's a lot of stuff going on. This is just a picture of what happens with respect to the shared resources. I didn't say what they want to do once they get access to these resources. So this is the model, and it's of the state space, and yeah, right. And I put in the deadlock is, by the way, it's that red dot under there. That means that one of them has access to something the other one wants, and vice versa. So that's a deadlock, and there's a symmetric point up there, which is an unreachable state. It's somewhere where no one can get, because well, yeah. So even if they want to do the same thing, if they have precisely the same kind of program along these axes, it can get quite complicated. And in fact, you can get all the complications you think you have with different programs along them. You can model that in also a symmetric way, just by sort of putting them at the end of each other. So here's capacity 1. So here I have all these squares. Yeah, they're squares, I guess. If I get capacity 2, there's nothing forbidden. I left the A's and B's there, but that's just for, well, decoration. So any questions about this? Because this is actually, I mean... What's the capacity? So the capacity is how many are allowed. So these forks, they allow 1 and only, and at most 1. So capacity 2 means at most 2. You can imagine, for instance, that you have a pool of printers, and you have 2 printers, so you can only 2 can print at a time. So yeah, so that's the capacity of a resource. Yes. So an execution is a path through this shape, through the state space, and it has to be directed in the sense that time has to go forward locally. So this means that T1 has to increase and T2 has to increase. So I have the green ones are allowed, the red one is not allowed. And then fortunately, when you're a topologist, paths like this, because of in this model, an execution is equivalent to another execution if they are homotopic. So that's great. So that sort of means that it's this local commutation, if you think about putting in little squares, that you can sort of commute yourself to it. So it's that equivalence that gets in there. But not only do they have to be homotopic, they have to be homotopic through directed paths, so through other executions. So in the plane, that doesn't matter. That doesn't make any difference. If you have 2 directed paths and they are homotopic, they are also directed homotopic. And of course with fixed endpoints, otherwise it's not fun. So here's, sorry, yeah.
And a homotopy, okay, that's just a path in the space of directed, there's nothing directed about the
No, and you can vary that. I mean, we have also sometimes we say that you should have the homotopic coordinate directed as well, and then you have to close off under zigzags. So that's another model. In these, when you model these Euclidean in your subsets of Euclidean space, it doesn't matter actually. So you can have both. So yeah. So this is a model, as you can see. I'm a Dane, and Lego is our thing. So I built it in Lego in my office, and then I took the picture out to the hallway, so you don't see my office for various reasons. So this is a 3D model. The red ones are obstructions, so they are somewhere where they represent some resources that have restricted capacity, and there's the red one in the middle is supposed to be floating, which of course it isn't because it's Duplo, but still you can imagine. So if you look at this and you look at this sort of yellow one where the arrow, the one that I point to with the arrow from above, if this was, if you were allowed to do a just a normal homotopy, you could sort of move it out here and then back again to the light green one. And the light green one is supposed to go in front of this one and then sort of behind it up there. Can you see that? So they're both doing like this around these two red ones, the red sort of blocks like this. The yellow ones are just to keep the elastic bands in place. They're sort of the start and the end. And you're supposed to go this way and that way and up. So you could do that in a non-directed way. These two would be equivalent, whereas in a directed way they are not. So in dimension 3, it's actually different, and Eric Goubot has made an example of a program where this is actually where these are not equivalent, so it is a real problem. So you should go for directed. So that's, yeah.
So these bit that they're not directed equivalent, because that homotopy that you would do...
Yeah, in the middle, when it has to go this way around this obstruction in the middle, it has to go like this and then back to get the right way around the red one, the tall red ones. And the tall red ones are supposed to go all the way through the shape. So
that wouldn't be a directed.
That wouldn't be a directed path. In the middle, it has to do a little wiggling like this. So yeah. So yeah. So you see that? Yeah. So this is actually it's not just algebraic topology. You need it with a twist. This directedness. So that's yeah. So that's the field we work in. That's the model we have. So what do we want to do? Well, we want to or what do the computer scientists want to do? They want to classify executions and up to equivalence. So what does that mean? That means to calculate components of the space of directed paths and give a representative of each class. Why? Well, because if you want to verify that a program does what it's supposed to do, you can now do it just on a representative of each class. So that cuts down the time you need, if the time you spend on classifying them is not too much. So that's sort of the other thing. This space of execution or path space, what do we mean by calculate? Well, Christoph will tell you something about giving a model of this and something with permutohedra, but that will be later. There's also the question of equivalence of programs, which fortunately has to do with the coverings, so directed covering. So now, again, fun, right? And good math. And we want to combine programs and infer properties from subsets. We study symmetry. If you have loops, you sort of repeat stuff. How can you use what you already know by going once around the loop to reason about what happens if you go more than once around a loop? And if you have more than one loop, you have tori and so on, tori with holes in them. So, and then this that I already showed you before, if you have just one thread and you want one program and you run it in parallel with itself, can you say something about the properties of this with itself as many times as you like, just in terms of sort of, do you know how to make sure that nothing goes wrong no matter how many times you run it in parallel with itself? We know a little bit about that as well. So these are some of the things we want, and then of course for the fun of it we want to understand the mathematics, so these sides going into it. So yeah, so I guess that's what we want to do. So what what is the model of, there are several models of what we mean by a topological space and then this direction. This is Marco Grandis' version. It means that, so you have topological spaces, and then you point to some of the paths and say you're a directed path, you're a directed path, you're a directed path. So I have a subset of the paths. And the paths are considered as just maps from the continuous maps from the interval, the unit interval. It has to be closed under concatenation. Makes sense, right? If you're directed here and you're directed here, you're directed all the way. It contains the constant paths. That you can, that's debatable, but well, we want our executions to be able to just stand around for a while and do nothing. And then it's closed under taking subpaths. So if you're directed from here to here and you only want to run a little bit of it the way, then you're also a directed path. And you can reparameterize them in a if you have an increasing reparameterization, it should also be closed under that. So it's not just any subset you can use. You should be a little careful with the reparameterization. Martin Rausen and a student of ours have written something about that. I mean, because there's so many maps from the interval to the interval. Even if you have a reparameterization of a path is directed, you may not have the path itself is directed, and that's because you can have some very nasty ways of, in the reparameterization of stopping along the way. These stop sites can be a cantoset and all these, and very ugly things. There are many, many, many maps from the interval to the interval. So, yeah. So this is one model. There are other models. We had another one in the beginning. This is sort of the one with nice categorical properties and so on. So
you assume that they have to be strictly increasing?
No.
So what takes care of not going back?
Well, that's this. If one way of defining what you mean by the directed paths is if you have on your space you have a partial order. And then a directed path is one which is increasing with respect to the partial order. So on the examples I had before, I would have the partial order on Rn or on the cube to the n. So then that's it. But it's just that there are many, many more in there. You can imagine other things. You can also say that reverse time and go the other way and so on. So that's so it's a much bigger category than just the ones you get from partially ordered spaces. And actually, the reason why we can't just have partially ordered spaces is what I drew up there. If you have loops, it's not a partial order. And there are other ways of describing this. Instead of saying that you want to have the set of directed paths, you could also have sort of a local relation, and it has to be a pre-order, so it has to be reflexive and transitive, but not necessarily symmetric. So if you have that and you have it locally and it combines nicely, and in fact it's co-sheaf conditions, and GV tells me so. Then you can. That's another way of doing it, and that's exactly this is more or less the same as the directed paths model. So the trivial destructive ones, if you have all of the paths, well, boring, but still. You can have the discrete destructive where you only have the constant paths. Again, boring. Computer program doesn't do a whole lot. But it's, but of course these get in there. Once you want to have a nice category, you want to have limits and stuff, you get these. So, yeah. But I mean, the thing with the loops is, of course, where where it gets interesting. So I should. Maybe you've had a few of those on the introduction to examples. So this is the only bit of this that I'm going to tell you about that is more or less my work. I had, together with one person. So I had this idea that instead of thinking about these forbidden areas where you can't go, you could also say that this is just a directed structure. This is if you only allow the constant dipaths in there, I mean, it's the same as saying that it's a black hole. Or it's not a black hole, it's not attracting. You never get there. I mean, you could also, even if you said you only allowed the constant paths on the boundary, you wouldn't get in there. So that would be more or less the same as cutting it out. So there is this connection between the set of directed paths, or this D-structure on the path. Whether you talk about a D-structure on the path, a D-structure on the space, or you talk about taking out subsets of the space. That could be the same game actually. And another thing where you might want to change your directed structure a little bit, you may want to think about what happens if you're allowed to reverse on small areas, such as the one I drew over here. If I can reverse a little bit, then I can get up and under. But maybe, there's a whole business of reversible computing, and I'm not claiming this is a real contribution to that, but it's still, you can think about that in this world also. So there are all these reasons of wanting to think about what happens if you change the directed structure in some ways. So, once you start thinking about that, you at least I did. I thought, what is this? The set of all directed structures on a space. What is that? What is the structure on that? What can we say about that? And this is. It's quite clear there's a partial order by inclusion, so that's sort of easy. But then once you have a partial order by inclusion, what else could you have? Well, I had a look in the literature, and there are lattices. I should have known that before, did not really. And there are ways of talking about this. This is a lattice. You can, that just means that you have in your partial order, you have a least upper bound, and you have a greatest lower bound. And the greatest lower bound is easy. You have these paths are allowed, you have these paths are allowed, then you take the intersection. If you have these paths are allowed and these paths are allowed, then you want the least upper bound by inclusion, then you take the union, but then you have to make it into a D structure. So that means you have to close off under concatenation and, which surprised me a little, also reparametrization, because you could say, you can reparameterize it. P is a D structure, Q is a D structure. Why do you have to reparameterize? Well, that's because if you just take concatenation, then you will get that where you change from something in P to something in Q will always be at specific times. 2 to 1 over 2 to the something, depending on which on how you do it. So reparameterization, you need that to move these times that you. Where you go from being in P to being in Q. So, and of course you have this is bounded. The bottom is a set of constant paths. The top is a set of all of them. So, okay. So that's a bounded lattice. That's already something. And what else could you ask for? Well, it's complete means that you can take a whole subset of D structures and then take the least upper bound of that and the greatest lower bound of that. And least upper bound is called join, greatest lower bound is called meet. So it's complete distributed lattice. What else can you ask for? What do these guys do in this order theory? Well, there are other things you can ask for. You can ask for, so there are other properties of lattices, and it's big business in computer science actually. Lattices, Boolean lattices. Well, computer science is logic, and there are the other ones. There are other properties of lattices that they care about, and some of you may have heard about locales and frames and all these things. So, so I'm going to. I can see the next slide is not quite that, but I'm going to look at what kind of these properties do I have here. Well, so here's first a short observation on how much this reparameterization, how bad is it? Well, the reparameterizations I have to do, remember the ones I had, Martin has this theorem that reparameterization, you should be a little careful because they can be really ugly. But the reparameterizations I need here are just piecewise linear because I don't only need them to move sort of these times of shift points. So that makes it a whole lot easier. It makes it's easier to work with. So that's just if you work with paths and do we want more paths? Do we want this and that? You know that there is something to think about here, but it's not since I close all my structures off under reparameterization, it's I've sort of I've gotten rid of that, so that's a good thing. So yeah, right. So well, I think I'll skip that. So what do I have here? So if I have a bounded distributive, I guess you can guess what that is. I mean, you have two operations, so distributive is what you think it is. So if I have one of these, it could, for instance, be a Boolean algebra. What does that mean? That means that I have a complement. So if you think about sets and by an inclusion, I mean, it's a Boolean algebra because, I mean, you have the complement of your set. If you take the union of those, you get the whole space. If you take the intersection, you get the empty set. So this is the sort of quintessential example of a Boolean algebra. If you don't quite have that, so and this is also, I mean, this is Boolean because it has to do with the reasoning with the true and false and so on. A Heiting algebra, you have a little less. So you do have, so let's just look at this thing with the pseudo-complement. So we talked about on the trip yesterday that I always have too much text on my slide. This is one example. Just look at the pseudo-complement. Well, no one said I had, but some people do. So the pseudo-complement is not quite a complement, but so it satisfies that if I take the intersection, I get the bottom of the lattice. I get, you think about the empty set. If I take the union, it's not guaranteed that I get a whole thing. So in logic, this is the thing that even if you know that the negation of A doesn't hold, you're not sure that A holds. So you don't have the, that's what it is in logic, it's the excluded middle. So actually these Heiting algebras, they're used in, they define, all of them define an intuitionistic logic. And don't ask me too much about that because that will get me, well, I mean, I can say the words. But it's, so it has to do with this, that you, this new kind of logic, it's what they use in type theory, just to say another word that I will not be questioned on. So an example of that is if you take the lattice of open sets of a space with inclusion, then then the pseudo-complement, I mean, you can't just take the complement because then you've left the lattice of open sets. Then you take the interior of the complement. So still, if you take the intersection, you get the empty set, but if you take the union, you don't get the whole thing. So this is an example of that. So so these are things they study in computer science and I guess order theory and stuff. At least the paper is published in something called Order, which everyone in my family finds very interesting. I have a publication in something called Order, but anyway. So yeah. So I do have a Heiting algebra here. So let's again the implication. Let's skip that because well, we need to get home today also. So the pseudo-complement is so I have a D structure, and then what paths are in the pseudo-complement? It's the ones that if I take a subpath, it's okay to take a subpath and then be in P. But then the way you be in P is in the trivial way, namely that you're constant. So that's precisely, you have to show that this is D structure, it's not that difficult. It's in general not a, in general it's not a complement because think about paths that wiggle an awful lot and then they're sort of increasing, then decreasing, then increasing, then decreasing. But I'm only allowed to do I only do finite concatenations here, so that doesn't work. So, well, it's actually a Heiting algebra. How close is it to being a complement? So why do I want to know that? Well, because these are the questions you ask in this order theory, but also if I have my directed paths, then can I add something and then think about the whole path space? It might help me to calculate these directed path spaces. So that's sort of the kind of question you'd ask in our setting. Well, so if I have a closed D structure, so what does that mean? It just means closed in the compact open topology. And I have some path. Then I can find a countable set of closed intervals such that when I restrict my path to that, it's in P. A countable set of non-trivial intervals, so not necessarily closed. So I'd say if I restrict to those, it's in non-P. And other than that, there may be sort of limit points. So think about that's where you wiggle your way into, where normally if you go a little bit to the left and a little bit to the right, you're neither in P nor in Q, nor in not P. So and you can find them. It's so it's sort of, well, so this means that I cannot think about the directed paths in terms of the sort of complement and then the whole thing. That will not work. So, well, right. And so it's a complement if and only if there, or you can say a path is in this the meet of these two, if and only if there are no limit points in that sense, if and only if it doesn't wiggle too much. So, and what does it mean? So is being a closed D structure, is that a real requirement? No, not really. So the standard D structure is closed. So yeah. So let me see. Well, we're getting to the end. So I think I actually want to skip to, well, let me just show you this. So this idea of thinking about the forbidden areas in terms of just restricting the D structure and say, well, I just think about this forbidden place as being something where I only have the constant paths. There's actually, there's actually an adjunction, or it's a Galois connection, or these are left and right adjoint functions, or whatever, the way you want to say it. If you take the subsets under inclusion and then the opposite direction, so say you have a subset here, so this is my subset, and look, there's a small crack in it. Then I take the paths, then I say, okay, over here I have constant paths in there, and then all the other paths around it. And then what is the adjunction? Well, it's take, now you have all these paths and see where they cannot where they cannot get. Well, you fill in the crack in that if. So there's an increase in the size of the subset when you do this. First take look at yeah. So, and in the other direction, if you start with a set of paths and see which ones are where are they constant, then and then you add in other paths which are constant in the same other paths which do not enter in there, then you get again you increase in the lattice. So well, so there's a kind of nice so that part worked actually. There is this nice connection. So yeah. So any questions for this? Otherwise, I will shift to a totally different thing, actually. Yes?
Px is the set of paths in a fixed D structure?
Yeah. So I start with sort of, I do it I think about actually starting with the usual structure on the cube or something, and then digging holes in that. So, but I could also do it with a hole with all paths. But I start with one, and then I just take what's below that. That's actually what I do. Yeah. Yeah. Yes. So here is something totally different. So this is what happens when you tell point process people about TDA first. So this is not work by me. This is work by Jesper Møller and Christophe Bijou, who's postdoc with us now. No, he's an assistant professor, I guess. So what they do is they have this is more or less Jesper's idea, that he defined what he's called the accumulated APF, accumulated persistent function. And everyone here who does TDA is going to scream in the middle in a minute. So what do? First, they make this shift, which we all do. You flip the persistent diagram, so instead of thinking about birth and death, you think about the mean age and the lifetime. So that's all okay. Why do they do that? They do that because all in this point process, they imagine they have all the points to start with, so they're all born at the same time, and they sort of get rid of that problem when they do this maneuver. So that's why. And then they add them up. So they add up the lifetimes, so C is the multiplicity. You might still have the multiplicity, and L is the lifetime, and then the indicator function. So they add them up. So this means they get this increasing graph, and here is for connected components, and here is for H1. And yes, everyone screams because this is, of course, unstable, right? You add up all the very small bars, and a lot might happen in the beginning, which, you would have thrown away had you been a TDA person. So, but they do that anyway. And one feature is that you now get a one-dimensional function. Other people do that. So for instance, Brittany does that, I think. Isn't that true? Yeah. And also, Fajstrup has a one-dimensional thing. And this means once you do that, you have all these different methods in standard methods in statistics you can use once you have these functions, one-dimensional functions. So, and this is just a list of a lot of them. They've used some of them, and I'm only going to show you a very small thing. One thing they've also looked at is this brain data that the Duke people have also looked at. So, I'm going to just show you a little thing. So, what they wanted to do was to say, can they get a new way of looking at point process, of distinguishing point processes? So this is here you can see, the one on the left seems to be different from the other one. The one in the middle is the Poisson process. It's CSR means completely spatially random. And the one on the right, I think, is sort of where you don't want to be close to your neighbors, which is sort of understandable, right? So if you do this, these persistent functions on these three, you do see some difference. And that's a good thing, but we already knew they were different. So why would they be interested in this? Because these, I think they already distinguish with some of the tools they already have. They have this thing called the Ripley K function, which is the probability of finding close to a point, finding other points in the radius R. So that gives you sort of a one-dimensional thing too. I think that distinguishes these things. But what they did was now they added some which are actually made to trick the Ripley K function. The one on the right is the Baddeley-Silverman cell process, and it's supposed to, if you look at these, the point process, people can look at these things and say, oh, that one's different from that one, whereas the rest of us are probably, the Matan one, I guess we can. So on the left, we have the complete spatially random. On the right, we have the Baddeley-Silverman cell process, which is supposed to, which is known to not be distinguished by this Ripley K function, and I think also by, I think that one F, I think that's the probability of having big empty areas. So yeah. So what they did was, can we test this against can we test whether these are completely spatially random? So they did all this, simulated a lot of them, and with different intensity and whatever you do. So you can look it up. They have a paper. It's in the archive. So here is so 0 is dimension 0, and APF is this accumulated persistent function. And what they claim is that it's really, really important to bring in the start ones, small components are important here, and distinguishing small components here. So so that's so this is assumed. So you see in the beginning. So and it does actually distinguish. So they have some results here. So so yeah, here's for each one. You can see the Matan is way down below, and you can. It's not difficult to see how this happens if you think a little bit about the topology here. So they have good detection with, so they combine them. As always, it's better if you combine them. They can decently detect this Baddeley-Silverman by using a combination of the Ripley K function and then this new accumulated persistence function, and so I mean, and they're happy, so that's good, right? So you can look it up, and you can talk to them if you want to. I mean, Jesper Møller knows everything about point processes. That's about it, I think. So I think everyone knows that Jesper knows everything. So and we're talking about other things too, but well, we'll see. Yeah. And here's a commercial. We have a book, Martin, Erik, Samuel and Emmanuel and I, and you can buy it, haha, and we will sign it if you want to. Yeah. I don't know, I will anyway. So actually, Emmanuel's grandmother, or his wife's grandmother, bought one, which I signed. So yeah, and this is of course a conference in Japan, which is organized by Rand, and you know, flowers and everything. So come, yeah, I think this is it. Right.
Questions for Lisbeth?
How much, I mean, I'm hoping I vaguely understood your directed paths thing. So you have these spaces of allowable paths
Yeah.
to some extent, and either you can think about you blocking things, you're adding more restrictions, or you're adding extra new things you can have because you've got crazy reversible
Right.
paths or something. Do you have a good sense of how much it can stand before it either becomes sort of everything? Does that make sense? Like how much flexibility can you add before the whole thing sort of just becomes trivial?
Yeah, that, I mean, so so that depends on your, I mean, if you put in abstraction first, I mean, then you can ask how much does it take to, I mean, get rid of this inability to go under or go over. So it depends on how your abstractions are, if that's an answer. I mean, so that would be one thing it could depend on.
Vague, so anything.
Well, here you go, you get a vague answer. yeah. So.
Is there a fast algorithm to actually, if you have given abstraction, how do you actually calculate the number of components?
Well, we have an algorithm. It's not really fast. I mean, that's the problem.
For like in R3 or?
No. This is in Rn, and then with yeah, and then with these and yeah,
The abstractions, how do the abstractions?
they are rectangular.
Rectangular and just would be some of those, or just a single rectangle?
No, and with all kinds of. I mean, they're also the Duplo model. You can do that, for instance, which is yeah. So things like that. So. And it finds that, and we also, by the way, this kind of thinking, they use this for, so what's it called? Seeing that parts of these, that some of these processes really don't interfere with other processes, because when this guy wants access to that resource, all these are prevented from doing it for some reason. So there are these independent things, which means you can take them apart and study them each one, which is also useful. Also, they say.
That, the algorithm works and you calculate the number of components. Is there a way of somehow grading which of these components are better than the other?
No, I don't think we think they're better. I mean, you can of course ask for. Yeah, I mean, some of the ones that are good are the ones that run along the edges. The ones or can be have a representative along the edges. That's called serializability. Because once you know you're along the edges, you know that the verification can be done just by verifying the serial program. So that you might want to do. So if you don't have anything sort of running through your shape, it's a lot easier to reason about it. So that's one thing that you could look for. Yeah. And
sometimes the decision might be made like, oh, maybe the left lifts fork and only one lifts, and then maybe one path is better than the other for some reason.
yeah, I mean, we do have. I mean, this is due to Martin. We have this thing that if there's a deadlock, you can reason about when are you bound to end up in the deadlock. I mean, I had this little square where you were bound to end up, and you can sort of find the unsafe, or I think it's not unsafe these days. It's something else. We call it something else. I've forgotten. So you can, and then just block that so that you don't go in there. So that's another thing we can do. But also, what they actually care about is these. inverse deadlocks, the ones where you cannot reach, because that means that you're guarding perhaps some state you don't like. So that's, you might want that as well. So, I mean, these guys, they control nuclear power plants and stuff, so, well, just to make it more interesting. Yeah, Mikael?
So I find myself getting stuck a little bit with this side comment for Miller's work.
Yeah?
About the noise not being important rather than.
Yeah, it's not noise, it's signal.
Well, the thing what I'm wondering is this from the point using this to characterize point processes perspective, or do they claim it to be applicable to the sort of classical inferring topological structure kind of perspective?
Well, they used it, do you know the brain tree data? There's this brain tree data which coming from some MRI scan or something. And you have this, so they used it to analyze, they used a height function, and then they analyzed this, and actually adding this, using this accumulated persistent function, they can tell the difference between men and women. Yay, hooray! So, which is of course brilliant. So, so they do better than what there's this paper by so it's Paul Bendich, and are you in it? No, maybe no. I think about Kate. No, you're not on that one.
I was going to say, I know the archive, I read the archive paper. And
Yeah.
one thing I thought was very cool is that they found a faulty data set because it looked too wrong.
Yeah.
And then they went back to the original data set and they discovered it was missing a chunk.
Yeah. Yeah, I mean, you can see there's this, if you actually look at the picture of the brain, of that brain tree, there's this sort of blur over here. And it's not because this guy blew his part of his head off, it's just that it's not in there. So if you put that in there, clearly there's
Things were so wrong.
yeah, and it's not even a woman, you know. So, yeah.
So really, so I'm still not clear on my question, because sort of with this classical perspective, trying to infer homological information about a shape with some sampling scheme on it, we really do have, in some sense, reason to believe that short intervals, especially higher persistence short intervals, are connected to irregularities in the sampling more than the topology we're trying to infer.
Yeah, but, I mean,
The sampling here wasn't a point process, or like they weren't sampling the points of it. They were using the graph, like it was already reconstructed as a graph.
yeah.
No, for example, you could imagine a time series for a stock exchange or something, right? And then you have a lot of very, very short bars. And
Yeah.
it's a statement about some version of volatility. Right? So,
Sure.
Yeah.
Right, so like the S&P 500, it has around 1 over L squared bars of length less greater than L. So
Yeah.
it's very small, you do have an explosion. That's the rate, and that's what you would have expected if it were a ground in motion.
Yeah. So it's so I guess you could say that it's just a different thing. I mean, you're looking for other things, so it's yeah.
But then
So
that's the
Yeah,
thing.
but there are
I
few
was
things
fishing
studied
for.
as precisely as mine.
Can I ask a question about the concurrence, the directed system?
Yeah.
So with these PV models, am I right that now if you took the D structure of all the paths in the excluded region, then the pseudocomplement is is everything that goes around the excluded regions?
Well, if you, no, the pseudocomplement is also, I mean, it's not only where the paths go, it's also the way they wiggle, right? So it depends on, I mean, if you take your usual, the square and then the usual direction and remove something, then in the pseudocomplement, surely all the paths within that forbidden area would be there, but also other things. I mean, the ones that run backwards outside and so on. So it's right. So it's more complicated than that. So yeah.
Let's thank the